Hello. In this video, I will be presenting some of the most characteristic flows that arise from the viscoelastic behavior of polymeric fluids. I have used a solution of polyacrylamide in water, dyed in a blue color, and pure water as a reference fluid, which is dyed in a red color. I will be looking at the Barris effect, the Weissenberg effect, the tubeless siphon, and the open channel siphon. I hope you enjoy. Firstly, we will be looking at the characteristic properties of Newtonian fluids and non-Newtonian fluids. Newtonian fluids are those whose flow behavior is described by a simple linear relation between shear stress and shear rate. This relationship is known as Newton's law of viscosity, where the proportionality constant mu is the viscosity of the fluid. Some examples of Newtonian fluids include water, oil, gasoline, alcohol, or honey. If we look at a graph of shear stress versus shear rate, we can see a linear increase in stress with increasing shear rate, where the slope is given by the viscosity of the fluid. In reality, most fluids are non-Newtonian, which means that their viscosity is dependent on their shear rate or the deformation history. In contrast to Newtonian fluids, non-Newtonian fluids display either a non-linear relationship between shear stress and shear rate, have a yield stress, or viscosity that is dependent on their time deformation history. Non-Newtonian behavior of fluids can be caused by several factors, all of them related to structural reorganization of the fluid molecules due to flow. In polymer melts and solutions, it is alignment of the high anisotropic chains what results in a decreased viscosity. In colloids, it is the segregation of the different phases in the flow that causes a shear thinning behavior. The first characteristic phenomena we are going to look at is the Barris effect. The Barris effect, or dye swell, is a common effect in polymer processing. This occurs when a stream of polymeric material is forced through a dye, in this case, a small tube. Water will flow out of the orifice without swelling. The polymer stream is compressed when entering the small tube, and will swell back to its former shape and volume after exiting the orifice. This is a phenomenon directly related with the entropy and relaxation time of the polymer. Initially, a flow stream has a constant rate before entering the orifice, and the polymers within the stream occupy a roughly spherical conformation, minimizing entropy. Inside the tube, the polymer loses its spherical shape, becoming longer due to an increased flow rate. When the polymer stream leaves the orifice, the remaining physical entanglements cause the polymer stream to regain a portion of its former shape and spherical volume, in order to return to the roughly spherical conformation that maximizes entropy. Now we should look at the Weissenberg effect. The Weissenberg effect happens when a fluid behaves in a very counterintuitive way. Instead of being driven away from a spinning object, it starts climbing. Sharing in the flow of the liquid concentrically around the rotating rod causes the component of the stress normal to the circular flow direction to become greater in magnitude compared to the other two mutually perpendicular components. This causes the fluid around the rotating rod to contract and be squeezed up along the axis of the rod, and thus climb it. In the case of water, the fluid will dip down in the center. This happens because the water closest to the rod is moving faster, so the pressure here is lower than the pressure of the water at the edges. A tubeless siphon is another good example of non-Newtonian phenomena. A siphon is started by inserting a syringe into the non-Newtonian fluid. The syringe is then raised above the free surface of the fluid, but the siphoning action continues, in marked contrast to the entrainment of air and disruption of the siphon that is seen in a Newtonian fluid such as water. In the open channel siphon, after setting the initial flow, the polymeric fluid pours itself because of the polymer chains that are pulling the fluid out of the beaker. This is also known as the self-siphoning effect. I hope you have enjoyed. Thank you.